Hey guys, and welcome to my A-level physics revision video, continuing with section 1, this video looking at the particle zoo. So firstly, I want to talk about cosmic rays. Every day the Earth is bombarded by what's known as cosmic rays, which are high energy particles that have come in all the way from space. And when they enter the Earth's atmosphere, they actually create new short-lived particles and antiparticles, as well as photons. Now, what are these cosmic rays? Well, cosmic rays were found simply to be fast-moving protons. It's when they collide with the gas atoms in the air, that's when we actually start to get these new particles. Now, these new particles are very short-lived and they decay almost instantaneously to either protons or electrons or neutrons, and so as a result we didn't really know about them until quite recently, but they are there, and they were discovered around about sort of the 1950s kind of time. So what are these new particles? Well, let's firstly introduce the muon. Muon has been given the symbol mu minus, a bit like the electron, got the little minus up here. And it's negatively charged, and it has a mass of 200 times the mass of the electron. And they also found this other particle called the pion. There are actually 3 different types of pion. There's the pi plus, there's the pi 0, and the pi minus. So these are 3 different types of particles. And the sign on the pion actually indicates what the charge is. So this is, of course, a positive, and this is neutral, and this is negative. And they have rest masses that are more than the muon, but less than a proton, so they're kind of between the muon and the proton. And finally we have the kaon, which has been given the symbol K. There are actually 4 different types of kaon. There's the K plus, there's the K minus, and there's actually 2 different types of K0. And when we actually come on to look at the quark composition of kaons, then we'll actually discover why there are 2 different types of kaons. But yeah, there are 2 different types of kaons, and fairly obviously the K plus is positively charged, the K minus is negatively charged, and the K0 is neutral. And as for the mass, well, it's more than the pion, but still less than the proton. So if we're going to order all these particles, then it would be, well, the electron would be the lightest, and then you'd have the muon up from that, then the pion, and then up from that is the kaon, and then the proton, and the neutron, which is a little bit heavier than the proton. Not by very much, but a little bit. So that's the order of masses for all the particles that we know. Now, all these particles decay very quickly, and here's how each one does. So let's start with the kaon first of all. So the K plus meson decays into a anti-muon, this is right there, a bit like with the positron, we used E plus, but the anti-muon has been given the symbol mu plus a mu neutrino, or it can either decay into a positively charged pion and a neutral pion right there. So those are the 2 different ways in which the K plus kaon can decay. So what about the K minus? Well, the K minus kaon will decay into a normal muon. So that was an anti-muon right there. This is a normal muon, plus instead of a normal mu neutrino, we get an anti-mu neutrino right there. And similarly, the K minus kaon has the other way, which is rather than pi plus, it will decay into a pi minus meson. And of course, the pi 0 meson. So that's the ways in which the Kaon can decay. Well, what about the Pion? Well, the Pion actually has 3 different ways in which it can decay. So say we start with a pi0 meson, a neutral pion. Well, that can either be converted into an electron, a positron, plus also a gamma photon, or it can just simply be converted into 2 gamma photons. So rather than having 2 particles, I can either have 2 particles plus a gamma photon or 2 gamma photons. And what about the charged pions? Well, the pi plus or minus will decay into a mu plus minus plus a anti-mu neutrino. So this plus minus basically describes, it basically says that if it's a pi plus meson, then it'll go to a mu plus lepton or and an anti-mu neutrino. But if it's a minus, then it will go to a mu minus. And so that's the pion. And finally, the way in which the muon can decay. A muon can decay into an electron and an anti-electron neutrino. And that would be if it's the negatively charged muon, and a positively charged muon would decay into a positron plus a normal neutrino. So don't worry too much about remembering all these decays. There are actually some laws which we'll talk about a little bit later on, which actually make all of these decays make a lot more sense, and you can predict what particles are going to come out based off of laws. So don't worry about having to remember all of these reactions. And in all of these decays, the quantities of energy, momentum, and charge are all conserved. So we have energy, momentum, and charge, and they are all conserved. And conserved just basically means that these quantities are exactly the same before and after the decay takes place. So now we're actually starting to get quite a few new particles, and it's what we're going to need to do at some point is we're going to actually have to sort all these out. So how do we do that? Well, we start by taking all the particles and we need to split them into 2 different categories. And so if we draw a little tree diagram right here, so we have all particles and of course antiparticles. They are all divided into two different categories. Actually, it's not quite all particles. We're actually not including any of the bosons. So this isn't including gauge bosons such as the photon, the gluon, the W plus minus boson. They actually have a category of its own. But we'll start by having a look at all particles and antiparticles, and they can be divided into either hadrons or leptons. And so what are the difference between hadrons and leptons? Well, hadrons are defined. They are defined as particles that interact with the strong nuclear force. Whereas leptons are defined as particles that don't interact with the strong nuclear force. However, both types of particle interact with the other 3 forces, but it's just the strong nuclear force that only applies to hadrons. Now, all other hadrons apart from the proton are actually unstable and will decay via the weak interaction into a proton. Now, hadrons are actually subdivided into 2 more categories, which are baryons and mesons. Now, baryons include things like protons, neutrons, And other baryons, for example, there's the sigma baryon. That one you don't really have to know anything about, but the only two you do need to know are the proton and the neutron, which are, of course, what make up the atom. And they're types of baryons. But all of these other particles, like the sigma, there's going to be others, but they're all very short-lived. And what about the mesons? Well, the mesons include the Kaon and the Pion, and there are also some others as well. But again, the only two you need to know about are the Kaon and the Pion. Now, it was actually found that baryons and mesons can actually be divided even further, or not divided necessarily, but the proton-neutron can actually be even subdivided into particles called quarks and antiquarks, which we'll come on to in a little while. But for now, I want to discuss energy conservation in particle collisions. Now, the Large Hadron Collider, which looks probably nothing like, but in principle, it's a giant ring. And what happens is it uses magnets to accelerate charged particles, causing them to smash into each other. So say we have two particles. They're accelerated to very nearly the speed of light. It's something like 99.99999% of the speed of light. And they're accelerated to such a high speed, and then they smash into each other. And what actually happens when they're smashed into each other? Well, you actually get new particles flying out of the collision. Now, since these particles are moving very, very close to the speed of light, then the actual classical mechanics don't apply in this particular situation. You actually have to go to Einstein's theory of relativity to describe the dynamics of the collisions. And the main equation that he came out with, and this is a simplified version, you only have to know the simplified version for this part of the course, but he said that the total energy is equal to the rest energy, which is E0, plus the kinetic energy. And for this kinetic energy, do not use a half mv squared. It does not apply in this particular context. So from this, you can actually work out what the rest energies of certain particles are. If you know the kinetic energy, you can actually work out the rest energy. Since you know that using the conservation of energy, the total energy before, energy total initial, is equal to the energy total in the final. So that means that E0 initial plus EK initial equals E0 final plus EK final. And so if you know these values, you can simply substitute them in before. And so say if it asks for the final kinetic energy, you would therefore subtract that away from that, and then you with the numbers given, and then you'd end up with the final kinetic energy, for example. But yeah, that is essentially what is happening at this level. You're having very, very fast moving particles, they're smashing into each other, and they're creating products. So I hope that helps, and I'll see you in the next video.